Hi, welcome to my pre-end semester presentation. In this video, I'm going to be talking about my work with Project 1, which is using inverse kinematics for gait analysis. I'm going to begin by showing you the data that comes in using multi-camera reconstruction by which we estimate the position of the patient's legs. Here you have the text graph that these cameras generate. You can see the first number is actually the frame, the next number is the LED number, and the next three numbers are the X, Y, and Z coordinates of that particular LED. The first six LEDs correspond to positions on the right leg. LEDs number 8 to 14 correspond to positions on the left leg, and the 15th one is at the back, the 7th one is not being used. Just to show you a little more accurately exactly where these LEDs are, the 0th and 1st are on the foot, right there. The 2nd and 3rd are on the calf. The 4th and 5th are on the thigh. The 5th, 6th is at the hip, and the last one's at the back. And of course, the left leg has a similar placement of LEDs. Moving on to the program, uh, if I just run it right at this point, uh, it opens with a Gait Simulator page where you enter the frame rate you want to see the simulation program in. Then you enter the patient's height in centimeters and his weight. Um, if you run it at this point, you see essentially a simulation of, well, me walking, because that's who the data is for. Now, since it's a normal human being, you can see the walking pattern is pretty similar to a normal walking pattern, or at least it should be. When there are two legs on the ground, the program identifies it and goes black, and when it's a left swing, it goes blue, and on a right swing, it goes green. The next thing that the program generates is a table of graphs. Um, the first one is our ankle graphs, and these are actually generated extremely accurately with the calculations done so far. The right ankle range of motion is here, the right knee, the right thigh, and similarly for the left side, and then the abduction angles, which is the movement of the hip along the z-axis. What you see with the right ankle range of motion is anything below this, around this line, is plantar flexion, where the ankle's angle becomes greater than 90 degrees, and above it is dorsiflexion, where it's less than 90 degrees. Just to give you a rough idea of how accurate this data is right now, I'm going to show you a sample range of motion estimated for normal gait from a movement analysis lab in Frankfurt. And if you just look at the shape here, the gray area, which is the interval of normal gait, you can see how closely it corresponds to the shape that we've received from our graph, um, plus or minus a scaling factor. Uh, then the next graph that generates are the torque graphs, and there are going to be 6 on this page. These are right now generated very roughly. Essentially, all you're really seeing here is a small bump. This is where just immediately after the heel has struck the ground and the foot is falling, and there's a small positive torque to make sure the foot doesn't fall too quickly. And then there's a large depression here, which is the main torque generated downwards. That's to lift your heel off the ground when your weight is bearing down on that leg. And then again, the next flat bar is when the leg is swinging through the air, and again, there isn't really much torque there. But I mean, these calculations have to be made much more accurate, and that's the first thing I'll be doing over the next week. After that, I will be working on recalculating the force, and this is actually a lot more difficult than calculating the torque. The torque was essentially a simple I alpha relationship. I estimated I using anthropometric data for the radius of gyration. It's given as a fraction of the segment length of, say, the foot or the shank or the thigh, and of course relative to the center mass or relative to the joint. So all in all, with a few basic assumptions that don't really take away from accuracy, the torque is pretty easy to generate. However, the force is a lot harder, and I think the reasons are fairly obvious. If I just draw a stick figure ankle over here, you can see that the difference between a torque generated from a muscle and a motor primarily comes from the fact that there are 2 points of force being acted. So whenever you have a generated net torque, you need to consider exactly whether it's 10, 0 or 20, 10, exactly what ratio these muscles are acting in. The second complication is because as the angle changes, I think it's pretty easy to see that the load arm is getting smaller because it's getting closer to the fulcrum. The fulcrum is at the ankle, and as the foot angle changes, it's getting closer or further away from that fulcrum. Um, so once the force is calculated accurately, I hope to be able to simulate gait under certain interventions. Say, for example, if we want to strengthen a particular muscle, I'm hoping that my program will be able to show exactly how the patient will walk under those conditions. Or if one particular muscle is spastic, say, for example, this muscle is spastic, and it's not allowing this muscle to pull the joint in that direction. And if we cut that muscle or if we strap a joint, exactly how the patient will walk under those conditions as well is what I hope to do in the next 3 weeks. And that concludes my work with Project One. The next video I'll be talking about my work with the pressure mapping system for the patient's soul.